All right, so 15.4, part 2. All right, so we're going to talk about Green's theorem and area today. So, we said yesterday that Green's theorem tells us that line integral around a closed curve of c, and we said m dx plus n dy equals the double integral enclosed by the region of the partial of n with respect to x minus the partial of m with respect to y dA. So we can turn a line integral into a double integral over the region that's enclosed by the closed curve. If, and we did an example where this came up yesterday. If the partial of n with respect to x, this integrand, minus the partial of m with respect to y equals 1, then this line integral reduces to becomes a double integral over our region of dA. And the double integral over a region of dA is the area of our region. So if we can arrange it, if we have a region we're trying to find the area of, if we can arrange it so that this quantity equals 1, we could use a line integral to find the area of the region. And depending on the regions, that can be much easier than doing this double integral to find the area. So there's several ways that we can arrange it so that we can use a line integral to find the area of a region. So what we're going to do is, what we're doing is kind of running Green's theorem in reverse. Normally, the usual way that we apply Green's theorem is to simplify evaluating this line integral, because a double integral over the region is easier to evaluate. We want to, if we have a difficult area evaluation because of the boundaries of the region or whatever, we want to turn that area calculation, finding the double integral over a region, into a line integral. So what we're going to do is, we want to arrange it so this quantity is 1. We want to pick m and n, so this quantity turns out to be 1, and then we can use a line integral to find the area. So we have a couple of ways that we can do this. If we let m, so we're defining this vector field so that we can use Green's theorem to evaluate the area with a line integral. So let m equal minus y over 2, or let n equal x over 2. And then we can use our line integral. So when we take the partial of n with respect to x, we get 1/2. Take the partial of m with respect to y, we get negative 1/2. And this quantity in our integrand becomes 1, and we can use the line integral to find the area of our region. So we're going to say the area of a region and this region is bounded by our piecewise smooth curve, bounded by C. C is piecewise smooth, and it's a simple closed curve. So I'm not going to write it all out, but C is a piecewise smooth, simple closed curve. And I should say bounded by. Then our area is given by 1/2 the integral, line integral around our closed curve, C, of minus y dx plus x dy. And we could split this into two pieces, and or we could also, so one choice of m and n is to let m equal negative y over 2 and let n equal x over 2. We could also pick let m equal negative y, and n we're saying is identically 0. So we're saying n is 0 everywhere. And in that case, then our area is the line integral over our closed curve of C of negative y dx. So when we use Green's theorem here, we end up with just 1 dA. And the third choice is, or let m be identically 0, so it's 0 everywhere, and n equal x. And then the area is hello. Pause this really quick. All right, so if we let n equal x, and m is identically 0, so it's 0 everywhere, then our area is the line integral around our curve of x dy. So we're running Green's theorem. So if we apply Green's theorem to this quantity, if m is 0 and n is x, then our partial of n with respect to x is 1. And Green's theorem tells us this line integral is just the area of the region. Same thing here. If m is negative y, then Green's theorem tells us that this line integral is the double integral of 1 dA, and we get the area of the region. Same thing with this. If we let m equal negative y over 2 and n equal x over 2, then Green's theorem tells us this line integral gives us the double integral of dA, which is the area of the region. So we can use Green's theorem to find the area of a region by evaluating a line integral. And sometimes, depending on your region, how your region is defined, it can be much easier to evaluate this line integral around a closed curve of this quantity, 1/2 minus y dx plus x dy, or this quantity minus y dx, or this quantity x dy. And it's much easier to evaluate that line integral than to evaluate the double integral to find the area. All right, so does everyone understand how we came up with these expressions? Just wanting to arrange things so that when we use Green's theorem on this line integral, it tells us all we end up with is a double integral over a region of dA. And that gives us the area of the region. Yes?
What do you equal signs
So this means it's identically equal to 0. So it's not evaluating to 0 at some point. So we're not evaluating and it's 0. It's 0 everywhere. So we're defining it as 0. So it doesn't count if we plug in some value of x and y and get n equal to 0 at a point. It has to be 0 everywhere.
Why can't you just set them equal to or identically?
So we're just defining them. We're just defining it this way. We're saying we want to find the area of the region. So let's pick some vector field so that when we do the line integral of the vector field, Green's theorem tells us that when I evaluate the double integral, I just get the double integral of dA. So I'm just picking these functions in a convenient way to make it turn out the way I want to. So for these, I'm picking it so that I'm saying that n is 0 everywhere. So that lets Green's theorem work out the way I want it to. All right, so let's look at an example where we could use these quantities to find the area of a region. So any of these three, and sometimes one is easier to use, one version is easier to use than the other. So any of these three can be used to find the area of a region. All right, so let's look at a region where this would be helpful. So we want to find the area bounded by this vector valued function. R of t equals t squared I hat plus t cubed over 3 minus t j hat for negative square root of 3 less than or equal to t less than or equal to square root of 3. So if we want to graph this, if we graph this in our calculator, I wouldn't know what this looked like without putting it in my calculator. This ends up looking something like this. And this point of intersection, so this gives us this curve, and this point of intersection is when t equals negative square root of 3, we're going this way, and then when t equals positive square root of 3, we hit that point again. So this is the point t equals plus or minus square root of 3. So that's we want to find the area of this region. So to set up a double integral, to find the area of this region, pretty difficult, because we need to set it up so that we have our either dy dx, something. It doesn't seem like it's going to work out well in polar coordinates. This would be a very difficult double integral to evaluate. So what we want to find our area, we want the double integral over r of dA to find the area of that region. It's a very tough double integral. But what we just figured out, what we just saw, is that the double integral, this double integral of r over r of dA, equals 1/2 the line integral around the closed curve of minus y dx plus x dy. So Green's theorem tells us that we can evaluate this line integral around the closed curve and come up with the area. And I'll write down the alternative forms as well, but I want to evaluate this one first. So x here is t squared. So dx equals 2t dt. Y is this quantity, t cubed over 3 minus t. So dy is going to be t squared minus 1 dt. And I substitute these in for my quantities x, y, dy, and dx, and evaluate that line integral. That doesn't look too bad. We just end up with powers of t in our line integral. And we're evaluating our line integral from t equals negative square root of 3 to positive square root. So let's substitute those in. This should be, should have a dA in there. So our area integral, so the double integral of r dA, using Green's theorem here, gives us the integral from negative square root of 3 to 3 of the quantity minus t cubed minus y dx. So t cubed over 3 minus t, and dx is 2t dt. Plus x dy, so this is going to be t squared times t squared minus 1 dt. And I can simplify this, distribute, combine like terms. I finally end up with, when I simplify that, minus square root of 3 to square root of 3. This simplifies to t to the 4th over 3 plus t squared dt. Not a difficult evaluation. Substitute in my limits, and this, when I do this, this is approximately 2.77. So this turns a very difficult double integral into a very easy line integral.
What about the 1/2?
Oh, did I forget my 1/2? Yeah, my 1/2 is up right there. And there should be a 1/2 out there. And if we evaluate this, so the 1/2 needs to be, I just forgot to write the 1/2 there. And we end up with 2.77. We could, yes?
So did you just pick for negative y dx plus x dy, so it works out?
Yeah, so if we can always pick, Green's theorem tells us, if dn dx, the partial of n with respect to x minus dm dy equals 1, then that this double integral reduces to the double integral of dA. So we're just picking m and n so that this quantity turns out to be 1. So that we can use the line integral to find the area. So we realize if we pick m is, if m is negative y over 2 and n equals x over 2, that quantity, this quantity, will turn out to be 1. So we just pick that to make it equal to 1. And we could also pick m equals negative y and let n equal 0. That quantity turns out to be 1. Or we could pick let m be 0 and n equals x, and that quantity, those partial derivatives subtracted, and end up with 1. We're just picking it to make it work out the way we want. All right, so the other versions of Green's theorem, the other two versions that we talked about, we could say it would probably be a little easier for this particular problem to say that our area is the line integral around c of x dy. That one's probably a little easier. And this one would turn out to be the integral from minus square root of 3 to square root of 3. So this is just the other way we could pick our m and n. This turns out to be t squared times t squared minus 1 dt. And this one evaluates, so we end up with t to the 4th minus t squared. And this one also evaluates to 2.77. And we could also pick, this one is not quite as easy. This one is probably the easiest one. x dy, just because x is pretty easy and dy is pretty easy. We could also say that the area is the line integral around our curve of negative y dx. And that one would give us the integral from minus square root of 3 to square root of 3 of negative t cubed over 3 minus t times 2t dt. And this one simplifies, doesn't simplify quite as nicely, but this also, when we evaluate this, we just end up with polynomials, powers of t, and this also comes out to the same answer, 2.77. So this one, for this problem, this one is probably the easiest. But they all get us to the same point. And they're all fairly easy. So what we're doing here is we're just arranging Green's theorem so that it gives us, the line integral gives us the area of the region.
Mr. Beaver, why did you ever use the first one?
I think the main reason I think of for this one is it's because this is more like the way we stated Green's theorem. We have an m and an n. We don't have to remember which one is 0. So this, I think this one is a little easier to remember, that you have both parts. But they're all three are equivalent. I think usually one of these two is easier to use. This one, and I think the books usually use this one because it looks more like looks more like Green's theorem, the way we wrote Green's theorem in the beginning. The other two just have the one line integral, so it doesn't look exactly like we wrote Green's theorem to start with. But usually one of these two is easier. This one definitely takes a little less algebra to get to where we can evaluate the integral. So just another useful extension of Green's theorem. Usually you're going to use Green's theorem to turn a line integral into a double integral. That's usually the application of Green's theorem. But we can use Green's theorem, and when we have a situation like this, we can turn an area calculation into a line integral around the closed curve. And for parametric equations, for finding the area enclosed by loops in parametric equations, using Green's theorem this way is a very nice tool to have. And I'm thinking of even sometimes with polar coordinates, where we're finding the area enclosed by a loop in polar coordinates. If we could turn that into a line integral, sometimes that might be easier than doing the integration that we did in when we used polar coordinates to find area. All right, other questions? Okay, now what I want to do for the end here is show you a couple of alternative versions of Green's theorem, and this is going to lead into where we're going for the end of chapter 15. So kind of a preview of the rest of the chapter, and also gives us a little bit of a glimpse we said we needed to wait until the end of the chapter to really say what the curl is and really say what the divergence of a vector field is. And this kind of gets us a little closer to being able to say what those things actually are. All right. So alternate forms. Of Green's theorem. All right, so for the first one, we talked about this one yesterday when we first wrote Green's theorem. For this first one, I'm going to let our vector field in three dimensions is going to be m I hat plus n j hat plus 0 k hat. So this gives us a field in the plane. Green's theorem works in the plane. Green's theorem is a planar theorem. And we're going to find the curl of f. Del cross f. So we're going to evaluate this determinant, this I, j, k, and our partials. So that's our curl. When we evaluate this, we end up with minus the partial of n with respect to z I hat plus the partial of m with respect to z j hat plus this quantity times k hat. Does that last quantity look familiar? What's that? Just a little bit. This is our integrand in Green's theorem. If I take the dot product of del cross f with k hat, so I'm taking the dot product of 0i plus 0j plus 1k. These two terms go away, and I just end up with the partial of n with respect to x minus the partial of m with respect to y. So we can think of this quantity that we've used in Green's theorem as the dot product of the curl of f with k hat. This is the vertical component of our field. Not of f, sorry, of del cross f. So this quantity, this dn dx minus dm dy, is the vertical component of the curl of f. And we can write, so by Green's theorem is telling us that the line integral around our closed curve of m dx plus n dy, and we also said that is the same as the line integral around our closed curve of f dot dr, is the double integral over our region of del cross f dot k hat dA. So what this is saying is that the line integral of the tangential component of f, so f dot dr is the tangential component of f around C. The line integral of that tangential component of f around the boundary of the region is equal to the double integral of the normal component of the curl. So the normal component of the curl tells us something about the tangential component of the field around the boundary. The normal component of the curl over the region tells us something about the tangential component of the field around the boundary. The curl is related to, the curl over the region is related to the tangential component of the field around the boundary. We will extend this to 3 dimensions at the very end. This will be in 15.8, and this will be, when we extend this to 3 dimensions, we'll get Stokes' theorem that tells us about the normal component of the curl over a surface and how that relates to the tangential component of the field around the boundary of that surface. So this is an alternative version of Green's theorem. We can think of this as what Green's theorem is telling us something about the relationship between the normal component of the curl and the tangential component of the field around the boundary. So a little bit of a preview of where we're going for the end of the chapter. All right, I also want to do this for the outward component of f around the boundary of our curve. So in the plane, we're going to look at the outward component of f around the boundary of the curve. So everybody more or less okay with what we did? Just trying to give us a little preview. All right, so we want to do the same thing for the outward component of f. So we want to talk about the around our curve. We want to talk about the component of the field that's pointing out is normal to the curve in the plane. So we're going to say our curve so our closed curve is given by r of t, and we're going to parameterize our curve. X of t I hat plus y of t j hat. And we're going around this curve from A to B. Our unit tangent vector on our curve t is r prime over the magnitude of r prime. And if we write that out in components, that's x prime over the magnitude of r prime I hat plus y prime over the magnitude of r prime j hat. So what we're talking about, let me draw a little picture here so we have a visual of what we're talking about. So we're in the plane. We have our curve C, some curve here. And we're traveling in the positive orientation, so we're traveling counterclockwise around the curve. At some point here, we have a unit tangent vector. So there's my unit tangent vector. What we're interested in is the outward component of f. So we're looking for a normal vector that points outward from the curve. And I'm going to call this our unit normal vector. So we've worked with these quantities before. And we want our unit normal vector to be pointed outward.
We need an ERT to the help room. We need an ERT to the help room.
In the plane, what was our shortcut for finding the unit normal vector from the unit tangent vector? You remember that back in chapter 12? What was our shortcut in the plane for finding the unit normal vector if we had a unit tangent vector? We're going to switch the x and the y and change the sign on one. So our unit normal vector is going to be given by n, and to make sure it points out, we need to change the correct sign, and that is going to be, and I'm going to use a small n here for our unit normal vector. And I'll write this with a small n. You can use either one. Our unit normal vector is going to be, and we need to change our signs properly, is going to be given by r prime, y prime over magnitude of r prime I hat, minus x prime over the magnitude of r prime j hat. So we need to change the sign on the y component. And if you need to draw some vectors and make sure to convince yourself that this is the right way to switch our signs, you can do that. But this is going to give us our outward unit normal vectors. And I'm going to put, and we want our unit normal outward. And we're going to let f, some field here, in the plane, is going to be mi hat plus nj hat, like we've been talking about. And we want to find the line integral. We want to sum this normal component of f around the boundary of this curve. So we're going to integrate this normal component of f around the curve. So we are going to evaluate the line integral around the curve of f dot in ds. So we want to sum that outward component of f around the boundary of that curve. So I'm going to take the dot product of m and our normal vector to get our outward component. And this is going to be the integral to evaluate this line integral from a to b. M dot n is going to give us m y prime over the magnitude of r prime plus minus n, got a minus sign there, minus n x prime over the magnitude of r prime times ds. So that's when we form that dot product, this is what we get. We're summing the outward normal component of f around this curve. What's our quantity when we evaluated scalar line integrals? What do we substitute for ds in terms of our? So if we wanted to evaluate the line integral of f of x, y ds, we parameterized our curve. And what was the quantity we used for ds? Magnitude of r prime. You're thinking of dt. Magnitude of r prime dt. So ds is the magnitude of r prime dt. So when I substitute this in for ds, the r primes, this should be an r prime. The r primes cancel, and I get that this equals the integral from a to b of m and y prime is dy dt minus n dx dt dt. The r primes in the numerator and denominator cancel out. Well, now I have a dt in the numerator and denominator. So this gives me the integral from a to b of m dy minus n dx. And I'm going to rearrange this so it's in the order that we talked about with Green's theorem. So this is the integral from a to b of minus n dx plus m dy And since we're going around a closed curve, this is the line integral around our closed curve of minus n dx plus m dy. We have Green's theorem that tells us that this quantity is related to a double integral. Green's theorem tells us what we do to evaluate this line integral using Green's theorem is we take the partial of this second quantity with respect to x, and we subtract the partial of this quantity with respect to y. So that's the double integral of r of dm dx plus, because I'm subtracting a negative, dn dy dA. How is this quantity partial of m with respect to x plus the partial of n with respect to y? How is that related to f? If f equals mi hat plus nj hat, this is the divergence of f. So this equals the double integral over r of del dot f dA. The divergence of f is a partial of m with respect to x plus a partial of n with respect to y. So finally, what we just figured out is the line integral around the closed curve of f dot n, the normal, the outward component of f ds, is the double integral over our region of the divergence of f. So the line integral of the normal component of f around the boundary of our region is equal to the double integral of the divergence of f over our region. So the divergence of our field is telling us something about the outward component of f around the boundary of that curve. Yes? Divergence is dot product. The curl is a cross product.
Oh.
Then that's what we did in the last example. So the divergence is telling us something about the tendency of the field to cause an outward flow, basically. So the divergence is telling us we get the field, we're summing the outward portion of the field around the boundary, and that's related to the divergence of our field. We'll extend this to 3 dimensions, and this will become our divergence theorem, and we'll relate the divergence over a 3-dimensional region. So we use a triple integral, and that will tell us about the tendency of the field to cause an outward flow through the surface of that solid region. It's kind of a preview of where we're going with these ideas. All right. Homework. The homework doesn't involve those last 2 things we talked about. Those are just to build us up for where we're going at the end of the chapter. Homework is more Green's theorem. All right, there you go.